Welcome, students. So after doing this modified Atwood lab, I know that we have collected some data and we have this graphical relationship where we have this net force. With an increasing net force, we saw this acceleration increase proportionally. And so we graphed it like so that way we could use this y equals mx plus b. On our y-axis, we have our net force. So we have our F net, and our F net is going to equal to our m times a, where the m is the mass and the a is that acceleration. So on the x-axis, we have the acceleration. On the y-axis, we have our net force, that's the total force, and our slope was the mass of the system. And then with this, I wanted to show an example question from the AP exam. So we have these students working together, experimenting about Newton's laws, just as we did. And they go through, and there's some key terms in here that there's negligible friction, and then the cart's initially at rest, and it's on a horizontal surface, and it rolls without slipping. And so the inertia of the cart's wheels is negligible, and it says that the students have access to the equipment that are common in a laboratory setting. So by collecting the appropriate data, we're asking which of the following graphs should the students produce to show the correct relationship. So we have these graphs over here, and we're seeing that as net force increases, the acceleration in the system increases proportionally. So this would be a question that's on that AP exam, and we can see how we used it to form this equation, this F equals to ma, the net force equals the total mass of the system times the acceleration of the system, and we can graphically show it as well here. And then from this, I want to get us into some free body diagrams and what this net force means. So this sigma F that we've been using, the sigma F, this is going to signify for the net force. So this net force, and what the net force is when we have all the forces added together. So all the forces get added together, and with that, that causes the mass to accelerate. Not just the mass, but the total mass to accelerate. So this net force causes the total mass of the system to accelerate. And so in this, we have these free body diagrams. And so we have this hanger, which we can call H, and this cart, which we can call C. And I want to try to get us into some free body diagrams. For the hanger, we know that it had the mass of the hanger times gravity pulling it down. So we just give it this m sub h times g. And the thing that was connected to it was this tension. Now we could use that F sub T or this capital T to denote this tension. And I tried to make this arrow longer because this was accelerating down, this arrow shorter because there was still a force up, but it was accelerating down. And that's why I made that arrow longer. For the cart, we had the mass of the cart times gravity down, and it was in contact with the surface. And so there's this normal force up. I can put in these marks of congruency. We know it was not accelerating in the y direction, but it had this tension that was pulling it. And this tension is the same as this tension. So I want to try to make these arrows the same length in proportionality. Then this will get us to this net force acting on the hanger, where it's only acting in the y direction. So that's why we have the sum of the forces in the y direction. So I have this tension up. So it's this tension up, that's why it's a positive, minus this mass of the hanger times gravity, minus mh times g, and that's going to equal, just for the hanger here, mass of the hanger times acceleration. That's the net force acting on the hanger. Now, for the cart, it has a x direction here, and we assumed that this was negligible friction. And so there were some parts about this that said that there was that this is going to be negligible friction here. And that was one of the assumptions we made in this lab. We can include friction, but it's easier at this instant to say no friction. So then for the cart, we have this tension in the x direction. and it's going to equal to the mass of the cart times the acceleration. It's the same acceleration that the hanger was accelerating with, same acceleration that the cart's accelerating with. The tension was the only thing that made the cart accelerate. So that's what this net force here. The only force, this is all the forces that made the cart accelerate in the x direction. Tension made the mass of the cart accelerate. But in the y direction, we have this normal force up minus the weight of the cart. That's that mass of the cart times gravity. That equals to the mass of the cart times acceleration in the y direction. It didn't accelerate in the y. That's why we can say this is 0. And that's why we can say this normal equals to the weight, because 16 minus 16 equals to 0. So that's why we were able to say that they're equal. Now from this, we could solve for the acceleration of the system. Now I'm not going to use this to solve for the acceleration of the system. I'm going to use the simplified way. I'm going to create a free body system for the cart and the hanger combined. I know that this is going to accelerate down. I know that this will accelerate down at the same rate that this cart will accelerate left. So I'm going to connect them. As I make a more simplified free body diagram, I'm going to connect them because they had the same tension acting on them. And I'm going to call this the hanger. I'm going to call this the cart. And I'm going to say that this direction here is going to be the same way that I have this cart, where I'm having now this mass of the hanger times gravity. That's the thing that's pulling the hanger and the cart. Pulling the hanger and pulling the cart was this gravitational force. So just like when you had the hanger and you had it on the table, the cart and the hanger did not move. But once you had it hanging, mass of the hanger times gravity was what made the hanger move and accelerate, as well as the cart. And we're having no friction here. That was one of our assumptions. So now we can use the net force, which is the mass of the hanger times gravity. That's going to equal to the total mass of the system, because we're talking about net force, mass of the hanger times gravity. That acts on everything in the system, the cart and the hanger. So it's the total mass, so the mass of the cart plus the mass of the hanger times that acceleration of the system. Now we can use this simplified, divide by the total mass on both sides, and that would get us to the acceleration. You could use this same setup down here. Since we know this tension is the mass of the cart times acceleration, then we can take this term, plug it in up here, which would be mass of the cart times acceleration minus mass of the hanger times gravity equals mass of the hanger times the acceleration. Bring this acceleration, which should be a negative term because it's accelerating down. Bring this over to the other side, turning it into a positive value. And then it's mass of the hanger plus mass of the cart times the acceleration would equal to this mass of the hanger times gravity. So you could do the same thing, but I find the simplified version, getting to this acceleration, much simpler. So now I want to try to take it to some more example questions that will be asked during this AP exam. So first, with this question here, we have a block that's being pulled along a surface of negligible friction. So once again, negligible friction is saying that friction is not going to be there. So, and I like to draw out the problems where I have this cart or a block. It's being pulled along a surface of negligible friction in a spring scale that exerts a force on the block. So I'm having this force F that's being exerted on the block. And then it tells us the mass of the block. So we know the mass is 4 kilograms, and the spring scale, which is applying this force F. So I know F is 10 newtons. And they're asking about which of the following free body diagrams can be applied here. So I'm going to draw in my free body diagram. I know there's mg down because there's gravity. It's in contact with a surface, so it's going to have this normal force up, and it has this force F going to the right. And so I have some values here. I know this force F has a value of 10 newtons. So I know that that has 10 newtons. And I know the mass here is 4 kilograms. So 4 kilograms times the gravitational field, which is that 10 meters per second squared, or 10 newtons per kilogram. So 4 times 10, so this will be 40 newtons. So if I see that that's 40 newtons, it wasn't accelerating in the y direction, so that means this also should be 40 newtons as well. So my normal force should be 40 newtons. And with that, I see that I need to fix my free body diagram, because this needs to be 4 times longer. The weight needs to be 4 times longer than that force. So if I try to draw that, I need to draw my weight, which is my m times g, and my normal force, which I can also put as this F sub n, and my force that's applied. I tried to draw this one 1/4 the length of this. I tried to draw this one longer, 4 times longer, 4 times longer. That would lead us to over here, where if we make our scale 10, then going to the right, that's 10, then down 1, 2, 3, 4, going up 1, 2, 3, 4, so that goes up 40. That's how we're able to get to this as our solution, but noting the scale. So now as we move to this next one, we're going to have these 3 identical blocks. When they say identical, they all have the same mass. So whatever mass the block X has, block Y has, and block Z has, so they're identical. And they're hanging on these identical strings, as shown in this figure. So which of the following free body diagrams represents the forces exerted on block Y? So as I do this, I'm going to put this dash mark. Put the dash mark around, so that way it kind of tells you, I know I have this string acting down and a string acting up. So that means I know I have to have some tension down, and I know I have to have some tension up. And further, we're on Earth, so there has to be weight. So I know that I have to have some kind of tension down, and I have to have some kind of weight as well. And I also need to have some tension up. But if I have these two going down, however much I have going down, I need to have it equal to going up, because this is not accelerating. So since it's not accelerating, however much up force I have, it has to equal to the down force. And if block Z has the same mass as block Y, then the tension from block Z is going to equal to the weight of block Y. So now that I have that, I need to have this force down equal to this force up. So as I bring it over to here, if I have 1, 2 down and 1, 2 down, that should equal to this 1, 2, 3, 4 up. So taking those two down equaling to the up, because it's not accelerating, and this tension down should equal to the gravity. So that's how I could get rid of this one, because this one doesn't have a tension down. My tension down should equal to my gravity, and it's not accelerating. This one here shows accelerating down, so that's not going to work. This one here is showing that it's also accelerating down because it's having more gravity and tension, and there is this upward force. So that's how we're able to get to that choice B. So now let's take it to this problem. So in this problem, we have then 2 blocks that are connected by a rope, and the mass 5 kilogram, 10 kilogram blocks. We have this upward force F that's acting on this upper block. So then we're given this question here: if the net acceleration is downward, so we're saying everything's going to be accelerating down, that means our net force needs to be going down. So that means we should have negative acceleration, a negative net force, if we keep with our standard positive and negatives for up and down. So we're asking which has a larger magnitude, the force F or the tension in the rope. So we're given this F and this tension in the rope. So that's what we're trying to compare, this F here and the tension from this rope here. So in order to get to that, there's going to be 2 steps that I'm going to follow. So I'm going to take first the entire system. As I take the entire system, I'm going to have, in this I see I have one force going up, and then I have these two blocks, and there's nothing, no ropes acting, going out, no ropes or anything. So as I get to this, I have my force F up minus the M of the 5 kilograms and the M of the 10 kilograms, or I'm just going to call that M total, the total mass, because the 5 kilogram is getting pulled up and the 10 kilogram is getting pulled up and pulled down by gravity, and this is going to equal to the total mass times the acceleration. So I'm going to take this, I'm going to solve for this F, and the acceleration is negative, so that's why I have my net force is negative. So I'm going to solve for this F. So this F is still this negative M total times A, and I'm moving the M total times G to the other side, so it's now M total times G, and M total and M total, so that allows me to pull out this M total negative A plus G. So now I have an expression for what this force is in terms of the mass, the acceleration of the system, as well as gravity. So the next part I'm going to take for the rope. I want to try to find the rope. So as I put the dash mark here, I have a rope going up and I have this gravity acting on the 10 kilogram object. So in that case, my force due to tension on the rope minus the mass of the 10 kilogram object times G, that's going to equal to the mass of the 10 kilogram object times the acceleration of the system. I'm going to solve for the tension in the rope, where the tension in the rope is going to equal to this negative mass times acceleration plus the mass of the 10 kilogram object times G. I can do the same thing I did before, pulling out the mass of the 10 kilogram object, now giving us a negative A plus G. So my tension in the rope has the same expression as the force pulling everything up, this negative A plus G, negative A plus G. The only difference here is the force of the rope has to pull everything, so it has to pull the entire system's mass. So that big force F that's pulling everything up has to pull both the 5 kilogram and the 10 kilogram object up, where the rope only has to pull up the 10 kilogram object. So that's why this M10, which is less than the total mass of the system, where the total mass of the system is greater than the rope, that's how we're able to get to this force F is greater in magnitude than the tension in the rope. And then as we move on to this part here, now we're given this F is 300 newtons. So now we know what the force F is, so we can use our F equal to this total mass with this negative A plus G. And now we know what F is, that's going to be 300. We know the total mass, that's 15 kilograms, the 10 plus the 15. And we're asked about the predictions of this acceleration. So we know that what G is, so now I'm just going to plug in some of the numbers. I know that we have 300 newtons, that's that force F, that's what's given in the problem. The total mass, that's the 10 plus the 5, so that's 15 kilograms, that's the total mass of the system. And we have this negative A, and we know the value of G. G is 10 meters per second squared. So now that we have that, I can divide by the 15 kilograms, so divide by 15 kilograms. That cancels that out on the right-hand side, so 300 divided by 15 is 20. 20 meters per second squared is going to equal to this negative A plus 10 meters per second squared. I'm going to move then this 10 by minus 10 meters per second squared minus 10 meters per second squared, giving us 10 meters per second squared is going to equal to this negative A. So what we see here is that this acceleration, which is accelerating down, just as we said before, accelerating down at this value of 10, which is our our acceleration of a value of g. So this acceleration here would be this value of g. And it's going to be going up because the acceleration is from that 300 newtons. What am I saying here? No, it's accelerating up. Not that one. So it's accelerating upward at that value of this g.